Welcome back. Time for physics. This is video lecture 30.1, first part. And I'm going to begin chapter 30, which discusses one of the most important physics concepts for modern technology for the last century. And it's the underlying physics that allows for almost all kinds of power production. In our modern technological world, we need electrical power constantly. The physics of this chapter is explaining how we produce electrical power in almost all situations. And so this chapter, chapter 30, is about the physical phenomenon called induction, or you'll also hear it called electromagnetic induction. To induce, that's part of that word, is to cause to happen. So there's going to be some way that we're going to cause something to happen. I know that's a bit vague, but that's what the word induction is implying. Now, a little bit later in the chapter, we'll introduce a new kind of circuit element, one that we haven't talked about yet. And this new kind of circuit element is going to have a new kind of circuit property, and that circuit property is called inductance. Okay? We'll learn about that later in the chapter. But the first part of this chapter is about the physical phenomenon known as induction. So let me start building up the ideas that we need to understand induction, electromagnetic induction. If I step way back to give a big picture, what I'm going to do is describe to you a new way to create an electric field, okay? Which will bring us up to a grand total of two ways to create an electric field. The first way to create an electric field is what we've been talking about for weeks and weeks now. All you have to do is have some amount of electric charge, Q. That's it. And you'll have electric field. That's the way we know. Here comes the new way to create an electric field. Have a magnetic field that changes with time. Now, there's a little more to it than that, but that's my big picture description. Have a magnetic field that changes with time. In fact, in this chapter, we see our first glimpse of the fact that electricity as a phenomenon and magnetism as a phenomenon are actually connected. Up to this point, we've never really talked about those ideas being related somehow, electricity and magnetism. This chapter starts to show us that electricity and magnetism are related. The hint here being that a changing magnetic field creates an electric field. I mean, if that's not a connection, I don't know what is. Okay? All right, now that's the big picture. We'll have a new way to create an electric field. But we got to build up to that. So let's step away from the big picture and just start with one new idea. Okay? So now I'm going to be talking about chapter 30, section 1. We're going to have some laws now named after various people. Okay? Michael Faraday is one of those persons, so we'll have Faraday's law. And then we'll also have something called Lenz's law. Faraday's law will be in part 1 video. Lenz's law will be in part 2. But I'm not even ready for those things yet. I need to step back yet and come up and talk about another idea. Okay? Another key idea. Remember the concept of electric flux? We've talked about that for a while now. And that idea is that if you have electric field in a region of space, and you've got a mathematical surface, might be a closed surface like the surface of a filled up balloon, or it might not be. It might just be a surface, say, inside a circle. which is not a closed surface. But if I have electric field that pierces that surface, I have electric flux through that surface. We calculated that, phi sub E, by doing what's called a surface integral. E dot dA over the chosen surface. Electric flux, piercing of a surface by electric field. Well, what's good enough for electric field is good enough for magnetic field. So if I can quantify electric flux as electric field piercing a surface, then guess what? I can have something called magnetic flux, which is a measure of magnetic field piercing a surface. Okay? The magnetic flux through a surface is a measure of the amount of piercing of magnetic field through the surface. So I started here with a little schematic showing a loop. Just a circle down there, okay? And the interior area there is a surface. Okay, so I have a loop, which is the boundary there, the circle, and then the interior region inside the loop is a mathematical surface. And then I also have magnetic field lines piercing through the surface. You can see them there. Now, they're at an angle. Okay, that's fine. But I have magnetic field lines, and therefore magnetic field, there's one of the magnetic field vectors, B, right there, piercing that surface. So I can ask about the magnetic flux through that surface. How do we quantify that? We imagine breaking up the surface into an infinite number of little infinitesimal area vectors, dA arrow. There's one of them right there. It's a little area patch. And by definition, the dA arrow that goes with that little patch is perpendicular to the surface at that point. All right, so I drew the little dA patch right there where the B vector was drawn. And so the magnetic flux right through that one little patch, which you could call, if you want, d phi sub B, will be the dot product B dot dA for that little patch I've drawn. That's a dot product of two vectors, B arrow dot dA arrow. And then to get the total magnetic flux for the whole surface, I add up all the d phi b's for all the little patches of area that make up that surface. And that leads me to this expression for the magnetic flux through a surface. I integrate over the surface B dot dA. It's called a surface integral, just like you would have with electric flux, except you're integrating magnetic field. So it's called magnetic flux, B dot dA. Now what's the SI unit of magnetic flux? Well, it must be the unit of B, magnetic field, Tesla, times the unit of area, meter squared. So the SI unit of magnetic flux is Tesla times meter squared. Note the SI unit of electric flux would be the unit of electric field, Newton per Coulomb, times the unit of area, meter squared. But now we're doing magnetic flux, so it's the unit of magnetic field, Tesla, times the unit of area, meter squared. And just so you know, for historical reasons, that unit combination of Tesla times meter squared is given its own name. It's called a Weber, WB. So you'll see that as well for the unit of magnetic flux, the Weber. But 1 Weber is equal to 1 Tesla times meter squared. Okay, that integral expression for magnetic flux is the definition of it. It is always the safe starting point for calculating magnetic flux. But you can do a shortcut if you have a special case that's applicable. And the special case is this. The magnetic field is uniform over a surface that is flat, and the magnetic field is perpendicular to the surface. So there's quite a bit of simplification there, but if that is the case, that might look something like this. There's a loop. And now let me shade in the area that's inside. Okay, there's the area. So that's the surface, I should say. The surface is flat. And then I have magnetic field lines piercing, uniformly spaced, and perpendicular to the surface. So that represents B, and this represents the surface. If we have all that going on, a flat surface, a uniform B, and the B is perpendicular to the surface, then that integral of B dot dA does simplify to merely taking the field magnitude times the area of the surface. And we'll use that shortcut when it's applicable because it's handy. But what I want to do is I want to actually just dive right into doing a calculation of magnetic flux. And I'm going to do that without practice first, because we've really done flux already with electric flux. It's the same idea, we're just using B instead of E. So let's go straight into what would really be more like a Wiley Plus homework problem that involves calculating magnetic flux through a surface, okay? Here's the scenario. We're looking down from above on a rectangular wire loop, and it's immersed in a non-uniform, so it's not the same at every location in space, and varying, that means, I should say, time varying magnetic field that is directly into the figure as indicated by the encircled X, labeled B. This loop has a width, W, of 3 meters and a height, H, of 2 meters. And here comes the magnetic field's magnitude. Magnitude. B equals 4 T squared X squared, with B in teslas, T in seconds, and X in meters. So note that this B magnitude function depends on both time, T, and position X. Okay? That position dependence means that at any given time, the field inside the loop does not have a single value. The field has a different value at different X locations. The field magnitude doesn't depend on the Y location, but it does depend on the X location. So if you were to freeze in time at one instant in time and look at different X locations, the B value would be different. That's what non-uniform means. Okay? We have a non-uniform magnetic field. But we also have a time-varying, non-constant magnetic field, meaning that at different time values, the B is different. Our task is to derive a symbolic expression for the magnetic flux through the loop. Okay. Well, I can't do that shortcut I just talked about. I do have a flat surface, right? The surface we're talking about is the surface inside this rectangle, right? Inside this rectangular conducting wire loop. Okay, fine, it's a flat surface. But the B is perpendicular to it, but the B is not uniform. So I really have to just start with, to get the total magnetic flux through that surface, the integral of B dot dA through that surface. And that means I have to imagine breaking up the surface into little area elements, dA. And those area elements, those vectors, dA arrow, have to be perpendicular to the surface. Well, the shaded surface there in yellow is in the plane of the screen. So the requirement on the dA arrow is that its direction must be perpendicular to the screen, so either towards us, out of the screen, or away from us, into the screen. And on a flat surface like that, it's completely our call. So I'm going to choose the dA arrow to be into the screen, the same direction the B is. That'll just make things a little bit easier. But what shape for dA? Well, base the shape of dA on how B depends on position. B depends on X, not Y, but X. So the little area element I want to pick is a rectangle that runs along the Y direction, the whole length, but is infinitesimally narrow along X. That's one of my little area elements. Okay? And it will have a width this way that is infinitesimal, dx, and a length crosswise of h. And it is itself located at some x coordinate. And so there's a little dA that goes with that, which I'm going to take to be into the screen. Let's write down an expression for the magnetic flux through just that little element. I'll call it d phi b, through that. That you would get by doing the calculation b dot dA. And so that's a dot product. Don't skip any steps. That means magnitude b, magnitude dA, cosine of angle between B and DA. They're both into the screen, so that angle is 0 degrees. The cosine of 0 degrees is plus 1. So my expression for d phi b, magnetic flux with that little strip, is B magnitude times dA magnitude. Okay? Where the B magnitude is that function that was given to me, 4t squared x squared. And the dA magnitude, well, that's just the area of that rectangle I've shaded in red. It's got a width crosswise of h and a width or length this way of dx. So the area, dA, is h times dx. So, let me scroll down here a little bit, and let me write my expression for d phi sub b now as, there's the B magnitude, and there's the dA magnitude, and let's just write that as 4h t squared x squared dx. And that's the expression for the magnetic flux through that one little rectangle. Then the total magnetic flux through the large rectangle, phi sub b, is to add up all the magnetic fluxes, d phi sub b, through all the rectangles inside that loop. And so that means I have to integrate 4h t squared x squared dx. Notice I'm integrating with respect to x from the x value at the left end to the x value at the right end. Okay? And so my limits on the integral are x values. And at the left end, the value of x is 0. And at the right end, the value of x is w. And I am to imagine that integral is done at an instant in time, freeze time, 1 instant. And then vary x from 0 to w. So what are the constants as far as the x integral is concerned? Because the constants can come out front. 4, of course, h, and t squared, because I'm to imagine doing this x integral at 1 instant in time. So then I just have the integral from 0 to w of x squared dx. That's not a hard integral. That's just x cubed over 3. And then put in the limits from 0 to w. And you have 4h t t squared w cubed over 3. And that's your symbolic answer for the total magnetic flux through that rectangle. And it depends on h, and it depends on w cubed, but it also depends on time, because the magnetic field did. So what we have here then, by the way, is a magnetic flux through a loop that is changing with time. That turns out to be a rather important concept, that you can have a magnetic flux through a loop that is changing as time changes, because that in fact leads us to one of the most important results in physics as far as technological applications is concerned, what is known as Faraday's law of electromagnetic induction, determined originally solely empirically by doing experiments, mostly by Michael Faraday in the 1800s. And what his series of experiments showed is that if you got a loop and you got a magnetic flux through that loop, and that magnetic flux is changing with time, just like that example I did, then in that loop you will have what we now call an induced EMF. Remember EMF from the chapter on circuits? An EMF is an energy source normally in a circuit that can drive a current, like a battery or a power supply or a solar cell, right? Or a wind turbine. Whatever it might be, an EMF supplies electrical energy to a circuit and can drive a current. The only way we've learned to have an EMF is like a battery or a power supply, something like that. What we're saying now is there's a new way to create an EMF in a circuit. Since it's a rather new way to do it, we give it its own name, induced EMF. And the way to do it, the way to have an induced EMF, is to have a magnetic flux through the loop that's changing with time. And that's what Faraday discovered through a series of experiments. I want to show you that with an actual video. I'll also show it to you in the class itself, but let me show you here, because Wiley Plus has a video demonstration of a person changing the magnetic flux through a loop, and then with a very sensitive device called a galvanometer, which can measure current, showing that you can get a current in a loop when the magnetic flux through the loop is changing with time. So let me now go to Wiley Plus, and I'm just queued up here to show you a video. Turn off the narration from the person, because I'll narrate it as we go. So that, in one hand, is just a coil of wire connected to the galvanometer he's pointing to. It's a little choppy. That's just a bar magnet right there, yes? That's just a bar magnet. And of course, every bar magnet is called a magnetic dipole. It's got a north pole and a south pole. The magnetic field, and it creates magnetic field. The magnetic field comes out of the north pole, goes into the south pole. And he's just going to move that bar magnet towards the interior area, the surface inside the loop. And then watch the galvanometer on our right, the needle indicator. See it move as he moves the magnet closer and farther away? That moving magnet is changing the magnetic flux through the surface of the loop. And when that magnetic flux is changing, you get a current through those wires. And that's what that galvanometer is detecting. Note that in that circuit, there is no traditional source of EMF. There is no battery. There is no power supply. Yet you can get a current, okay, when the magnet's moving. Notice now, he's holding the magnet right in the middle, but he's not moving it. Notice, no current then. He's got to be moving the magnet, because you have to have a changing magnetic flux. Now he's going to show you another way to get a changing magnetic flux. Another coil nearby. Now that one is hooked up to a power supply, and he's going to turn it on. And he did, and now he's going to move that coil closer and farther, closer and farther. And when he's moving the second coil, he gets a current in the first. Because the second coil, which has regular current in it, creates magnetic field, and when he moves that second coil closer or farther from the first, he's changing the magnetic flux through the first coil. And when you change the magnetic flux through that coil, you get what's called an induced EMF in that coil, and that's what gives you the current. He has to be changing the magnetic flux through the first coil. Okay? This really does happen. This is how we generally create electric power. Okay? All right. So now, let me go back to my notes. I'm going to state Faraday's law. Okay? First in words, then in symbols. The magnitude of the induced EMF, right? This is a special kind, a new kind of EMF for us. It's called an induced EMF in any closed loop. And it might be a physical loop, meaning conducting material that you can hold on to, like in that video, but it might only be a mathematical loop. It might be a construct, a mental construct, and not an actual physical loop. Either way, the magnitude of the induced EMF in any closed loop is equal to the magnitude of the rate at which the magnetic flux through the loop changes. Boy, a lot of important words there. Rate at which magnetic flux through the loop changes. And I'm just dealing with magnitudes the way I write Faraday's law. But here it is in symbols. Notice the symbol we're going to use for this new kind of EMF. Curly E, like we did for EMF before, but we're adding a subscript, IND, induced EMF, because we're creating this EMF in a completely new way. Has nothing to do with a battery or a power supply. So the magnitude of induced EMF in any closed loop is equal to the magnitude of the rate of change of magnetic flux through the loop. Rate of change means derivative, time derivative. So I take the magnetic flux through the loop, phi sub b, and I take its time derivative, d phi sub b dt. Okay? Now I just did a little mini example where I calculated magnetic flux through a loop that depended on time. See it there? I had an example where I had a phi sub b equal to 4h t squared w cubed over 3. So if I asked you, you ought to be able to do that calculation. Yes, for that phi sub b, d phi sub b dt. You ought to be able to do that. I'll let you think about that. So what Faraday taught us is that if you've got a closed loop and you have a magnetic flux through that loop that is changing with time, you'll have an induced EMF in that loop, which can in turn drive current if it's an actual conductive loop. And the induced EMF magnitude is equal to the magnitude of the rate of change of the magnetic flux. Now, a little bit of a special case. If our loop is indeed a physical coil made of conducting wire with N windings, then interestingly enough, experiments show, you get a factor of the induced EMF for each winding. So that to get the induced EMF in that case, you take d phi sub b dt, the rate of change of the magnetic flux through any one winding, and you multiply by n, the number of windings. And so if you'd like to get a big induced EMF, then take actual conducting wire and wrap it around a frame multiple times, and then change the magnetic flux through the windings. All right, now let me remind you that the general formula, the always safe starting point for calculating magnetic flux through a surface is to do the integral of B dot dA for the surface. I want to remind you of that because I want you to see how there are, in some general sense, three rather different ways that you can get a magnetic flux that's changing through a surface. And these three ways come from this very expression I just wrote down. Because the magnetic flux depends on B, it depends on the area of the surface, and because of the dot here, it depends on the orientation, the angle between B and the surface. So that's what leads me to state that there are three ways the magnetic flux through a loop can change. You can have the magnitude of B changing. You can have the area of the loop changing. Or you can have the orientation of the magnetic field to the plane of the loop changing. Or obviously some combination of these. So now let me show you animations that show you each way in turn. Okay? So now I go back to Wiley Plus. And I need to now show you an animation. Okay? So now you're seeing a representation of something that would not be too hard in the laboratory to set up. Very long, straight wire along the x-axis. It's got a current I flowing in it, but this current is going to be changing with time. That's not hard to do. All you have to do is hook up the wire to a function generator like we've used in lab. It's going to be a sinusoidal, this current, function of time in the wire. Just to the right of the wire is a rectangular loop made of wires and a resistor, and that pink box labeled A is a device called an ammeter that will measure current in that loop if there is any. All right, now I contend that there is magnetic flux through the area of that loop. In fact, see the green arrows pointing in the plus Z direction? Those are some of the magnetic field vectors through the interior surface of that rectangular loop. And so you can see, I think, quite directly that there is magnetic field piercing the inside of that loop, so you have magnetic flux through that loop. Now, if the current in the long wire, I, is changing with time, then the magnetic field it creates. And that's what those green arrows are, right? They're the magnetic field vectors from the current in the wire. Then the magnetic field vectors are going to change with time. But the magnetic field vectors are what pierce that inside area. That's what gives us the magnetic flux. So if those magnetic field vectors are changing with time, then the flux is changing with time. Bingo, Faraday steps in. Because I have a changing magnetic flux through that loop. So I'm going to run the animation. The current I in the long straight wire is going to change with time. So the magnetic flux phi sub B through the interior of that rectangle is going to change with time. And the animation is going to graph that magnetic flux and show you that it changes with time. It's changing sinusoidally. And Faraday says that if you have a changing magnetic flux, you'll have an induced EMF. So now let me reset, click Show More Plots, and it's going to plot the induced EMF and the current in that ammeter as a function of time now when I run the animation. All right, so mainly I want you to note that there's a magnetic flux through the loop that's changing with time, and because of that, there's an induced EMF. And the induced EMF is in the second graph. And I will just tell you that the second graph, the induced EMF, is given by the negative rate of change of the first graph, magnetic flux. There's a negative sign there. We'll be talking about that in the second video. But right now I just want you to observe that I've got a scenario where I've got a changing magnetic flux because I've got a changing B magnetic field. and I get an induced EMF. Now let me show you another way to get an induced EMF, or to get it because I have a changing magnetic flux. This picture shows a big solenoid with its central axis along the z-axis, and current I solenoid going around on the outside, the way that red arrow shows, which means it creates uniform magnetic field B in the interior of the solenoid. And that's the green arrow in the interior there. And now I'm going to have a loop. It's going to start it. It's a magic loop. It can change. It's going to be circular. It can change its radius. It's going to start with a radius of 0 at the origin, and it's just going to expand outward with an ever bigger radius and therefore an ever bigger area. And because I have a changing, and I'll have a magnetic flux through that area, and I'll have a changing area, so I'll have a changing magnetic flux. So first, let me just run the animation, and you can see that the magnetic flux will change with time. There's the loop growing. Notice, though, the magnetic flux stops changing after 3 seconds. You see why? I'll drag the slider back. There. Why does the magnetic flux graph show no change anymore, even though that loop is getting bigger? You see why not? It's because once the loop gets outside the solenoid, there's no more magnetic field out there, so the magnetic flux is no longer changing. All right, but I have a changing magnetic flux, at least for some amount of time, because of a changing area. Reset. Now I'm going to show more plots, and I'm going to see when there's an induced EMF in this loop. There it is in the second graph, but boom. The minute the flux is no longer changing, the induced EMF goes to 0. See that on the graph? The second the magnetic flux is no longer changing, the induced EMF in that loop is 0. That's therefore a situation where I have an induced EMF through a loop, because I have a changing magnetic flux through the loop, because I have a changing area of the loop. At least as long as that flux is changing, I have an induced EMF. Now lastly, let me show you, again, a big solenoid with a current I solenoid going around on the exterior, giving me a uniform magnetic field B in the interior, in the plus Z direction. And there's my loop. But now this loop is hinged on the x-axis. And when I start running the animation, it's going to rotate about that rotational axis along x. And that little that little blue arrow is the normal unit vector n hat, which will remain perpendicular to the plane of the loop. So let me just run the animation, and you can see the graph of magnetic flux now as the loop rotates. The magnetic flux changes because the angle between B and that n hat changes. And the flux involves a dot product of B and that n hat direction. So as the loop rotates, the angle between B and n hat changes, the magnetic flux changes. Now let me reset and click Show More Plots, and we'll see that because we have a changing magnetic flux, we'll have an induced EMF. Okay? And yes, that induced EMF graph is given by the negative of the derivative of the magnetic flux graph. But we'll talk more about that negative sign in the next video. I'm just showing you basically the 3 ways you can get a changing magnetic flux in a loop, and therefore an induced EMF in the loop. Have a changing magnetic field through it, B. Have a changing area of the loop, or the changing orientation between B and the area. All right, let me go back to my notes. And we'll do a little bit of practice together here. And that will be the end of this first video. Okay, a little practice with Faraday's law. We are given a graph here. Shows the magnitude of a uniform magnetic field B, but it's a function of time. And this magnetic field exists throughout a conducting loop. with the direction of the field perpendicular to the plane of the loop. So it's not even hard to draw something. I don't know exactly what the shape of the loop is, but I'll draw it as a circle. Okay? And then I've got a uniform magnetic field perpendicular to the plane of the loop. But it is a function of time. But it's that same magnitude at any given time everywhere through that surface. Okay? All right, that's the scenario. We are to rank the 5 regions of the graph, see them? A, B, C, D, E, according to the magnitude of the EMF induced in the loop, biggest to smallest. Magnitude of the induced EMF in that loop. Okay? You see that since I have a flat surface and a uniform B perpendicular to it, I can use the shortcut expression for the magnetic flux. Magnitude of B times the total area of that surface. Okay? Now Faraday tells me, through Faraday's law, that the magnitude of the induced EMF in that loop will be given by the magnitude of the rate of change of the magnetic flux through the loop, d phi sub b dt. So that means the magnitude of d by dt of b times a, where that b means magnitude. But it's only the b part that's changing, so I'm going to write it like this. A times the magnitude of dB dt. The a is just multiplying there and isn't changing. So it tells me that to rank the magnitude of the induced EMF, I just have to rank the magnitude of dP dt. But if I give you a graph of B versus T, then it's easy to think about dP dt. It's the slope of the graph. Absolute value. So I just look at the slopes, because that's going to tell me the rate at which B is changing. Which region has the biggest slope? Then next, and so forth. Try the ranking, pause the video, and then come back. Okay, did you say region B has the steepest slope? And that then D and E, remember I only need magnitude, so don't worry about the fact that the slopes in D and E are negative, and they're equal D and E, but they're not as steep as the slope in region B. So B is first, then D and E tie, and then there is no slope in A and C, so there is no induced EMF. So there, in those two regions, the induced EMF is 0. Okay? All right, that's just very brief practice. We're going to have to be doing a lot of practice in class with Faraday's law, and that's our first video for that class.